This will be a very simple talk. The basic reason is that I realized very early in my career that molecules are very complicated systems, and I could never become a molecular physicist because I was overwhelmed by that complexity. So I will tell you a much simpler story, which I hope will be suitable for just before the lunch break. And the basic question I would like to address, not to answer, is do you need to know quantum physics to do efficient optical communication? Okay. So what is our starting point? Basically, we will be interested in from the moment when digital information becomes analog. Electrical engineers call it modulation. Quantum physicists call it quantum state preparation, and we will have this ambiguous terminology all the way. So until the stage of demodulation, which a quantum physicist would call a state measurement, and we will assume that everything else in this picture is at the Shannon limit. We will not worry about how efficiently this can be implemented. And we will deal with a very simple linear channel model. Basically, we will assume that in each channel use, we are sending, let's say, an optical pulse with a complex amplitude. And two things may happen. We may rescale this complex amplitude. In the case if this rescaling is down, we will talk about attenuating or a lossy channel, but we may also amplify our signal. And on top of that, we will add Gaussian noise. So to relate it to physics, we will introduce some physical quantities. And let me introduce also the Planck constant, so I can define the energy of a single photon at the carrier frequency. And two quantities that we will be playing with is the signal strength, namely how many photons on average we will have per one channel use, which we will call also a slot, and how much noise in terms of photon number is also added on average per each channel use. So for now, this choice of units is completely arbitrary, okay? We could have measured this in any other units, and you may think that using this Planck constant here is kind of superfluous. But there is a very good reason for using these specific units. Namely, if we take standard photodetection, which at the fundamental level is measuring the number of photons in our incoming pulse, which are transformed in the same number of photocounts. Basically, if we use our photon number units, then the statistics is Poissonian with this photon number units as the mean for our distribution. Of course, I mean, if we have macroscopic fields, we do not see this granularity, but let's not worry about it. Furthermore, if we measure a single quadrature, or let's say real or imaginary part of our complex amplitude through homodyne detection, then we obtain this quadrature in the form of a Gaussian distribution, again with the width of this Gaussian distribution of the order of 1. And this choice of units is particularly nice if we decide to measure both quadratures by, again, what optical engineers will call phase diversity homodyning, and quantum physicists will call double homodyne measurement or a heterodyne measurement, because then what we measure is basically the complex amplitude of our input field with unit Gaussian width, okay? So now let's go to the task of transmitting classical information. We all know the Shannon-Hartley limit that tells us that the capacity is the number of real variables we have at our disposal log to 1 plus signal to noise ratio. And let's apply it to our model scheme. First, let me consider a more perhaps not a bit strange approach when we are just using a single quadrature to encode information. It's very easy to do the numbers and arrive at this single quadrature expression. If we do the same for two quadrature modulation by assuming that we have the same mean number of photons at our disposal, we obtain, of course, an expression that doesn't have this 1/2 factor simply because we have now two quadratures. But the main point I would like to make is that the two terms that enter the denominator responsible for noise contribution, they come with different weights, okay? We have one contribution that comes from that action, which we assume that is as good as it gets, that is at the shot noise limit. And then the second term comes from this excess noise added to the channel. So this is a first hint that it's difficult to talk about signal to noise ratio as a universal figure. We really have to think about a specific communication scheme. Now, if we plot these two expressions, capacity expressions, then assuming that we don't have excess noise, then we discover that actually for low signal strength, it pays off to use just one quadrature for modulation and forget about the other quadrature altogether. Of course, assuming that we have some phase reference. But this is the first hint that things are not completely trivial. To complicate things even further, let me propose a completely unpractical communication scheme, okay? Let's assume that we have a noiseless, lossless channel, and we decide to send information in the form of Fock states. We've heard already today about states, quantum states of light that have a well-defined number of photons. And in principle, we can define a pulse that carries exactly one photon, exactly two photons, or exactly three photons, and so on. So if we have a photon number resolving detector that is able to measure exactly the number of transmitted photons and our channel is lossless, if we are operating under the average power constraint, so we require that the mean photon number per slot or per channel use is at a certain level, it's very easy to optimize mutual information in such a case. And the expression we get is actually above either of those Shannon capacity limits, okay? By the way, this is a very specific example. It works only for unit transmission. If we try to use Fock states for communication over a lossy channel, you will not get very far, okay? So you may argue that this is actually a very theoretical scenario. However, if we now, well, not us, not me, but if smart people do complete quantum mechanical analysis of how much capacity has a Gaussian channel using the full quantum mechanical picture, we arrive at a very nice expression that was shown by Yanis in a slightly different form, which was first, well, it appeared first in a very seminal paper by Jim Gordon in 1960s, which was kind of educated guess. I mean, it is absolutely amazing that he got this formula by heuristic considerations. Later on, if you want to have a rigorous mathematical proof, this is a result from 12 years ago. And well, the main point I would like to make here is that if you ask me what is the signal to noise ratio in this formula, I can't tell you. I can't really tell you exactly where this ratio comes, because it depends both on the signal strength and the noise strength expressed in absolute photon number units. If you ask me what is the ensemble of input states, or what is the input constellation that saturates this limit for arbitrary channel transmission and for arbitrary excess noise, the answer in principle is very simple. We should just take a Gaussian ensemble of coherent states. But if you ask me what is the receiver that will get us to the capacity limit, all I can do is to tell you that I don't know. And there are some very complex, very sophisticated designs for such receivers, but basically this is equivalent to building a quantum computer. I think this is a challenge of the same order. But let me step back and ask a simpler question. Should we really worry? Should we really be concerned with this general Gordon-Holevo limit compared to regular Shannon expressions. So let us first forget about excess noise introduced by the channel. In this case, the quantum capacity, the Gordon-Holevo capacity is given just by the Gordon function. And if we assume that our signal is strong, then it admits a very nice expansion in terms of the inverse of the signal strength. In the first term, we simply recognize the Shannon two-quadrature capacity with shot noise limited detection, and we get a constant advantage of 1 NAT log 2e unit of information per channel use. So basically, this is the best we can get for a loss-only channel without excess noise for a strong signal, okay? This is what we can fight for. On the other hand, if we have strong excess noise, we can use the same expression as before, expand both terms using this approximate formula, and actually for strong excess noise, Gordon-Holevo capacity limit reduces to 2 Shannon capacity, to 2 quadrature Shannon capacity. Which means that if we have a lot of excess noise in our system, we don't have to worry about Gordon-Holevo capacity limit at all, okay? It makes sense to look more closely if we have very, very little excess noise in our channel. Then the second question is to be asked is whether our optical signal is strong in the sense of the mean photon number per slot. If it is, then we can, in principle, have 1 NAT of enhancement, 1 NAT per channel use, but don't ask me how to get there practically, okay? I'm withdrawing from this. But if we have very, very weak background excess noise in our channel, and we are dealing with very, very weak signals, then things may become interesting, okay? And let me keep you wondering about this limit for a second, because first I would like to tell you about a scenario when we have a lot of excess noise. We introduce it on purpose, and it helps a lot, okay? And this scenario, we are using this scenario every day, almost every minute of our life, basically, if we are transmitting data over long-haul links with optical amplification. So in this case, the standard that is being used, I mean, all the time is like erbium-doped fiber amplifiers. Let's assume that they operate at the quantum limit, which means that an amplifier with a power gain G has to add at least G minus 1 noise photons in per channel use. And one question one may ask is whether it makes sense to use this kind of amplifiers, or maybe get rid of them altogether and use this fantastic quantum receiver at the end of our channel. And the answer is very depressing for a quantum physicist, because basically the best thing to do is to use our noisy amplifiers, and then the advantage of using quantum receivers basically goes away. So the best strategy is to use amplifiers, to use optical amplifiers and standard 2 quadrature detection. But you may wonder about one thing. I'm sure many of you have heard about phase-sensitive amplification, which is quite often is claimed to be noiseless, because phase-sensitive amplification amplifies 1 quadrature with exactly the same factor as noise. It doesn't add excess noise to this quadrature. But the story is not that simple if you include quantum fluctuations, quantum noise, in the complete description of your system. Basically, if you include the fact that during losses, you get some environmental vacuum fluctuations in the budget. And in this case, actually, the story is very similar. We also have loss at the capacity of our link goes down. And the advantage of using quantum receivers is not that much either. However, it is quite interesting to compare phase-insensitive amplification with phase-sensitive amplification. Of course, for short distances, phase-sensitive amplification is not that exciting because we are using factor of 2 on capacity because we are encoding information in just one quadrature. But if we do the numbers, which is particularly easy for distributed amplification limit, because then we solve just some ordinary differential equations, then actually this drop in capacity is lower for phase-sensitive amplification, which means that at some point we get a crossover. Actually, we can put more information into our channels with phase-sensitive amplification, okay? So this is the case of very noisy channels. If we want to do communication with very, very little noise and with very, very weak signals, we can, since 2023, we have an opportunity to receive information from a Psyche mission that was launched at that year. And in addition to a regular large radio frequency antenna operating in the X-band, it was also equipped with a deep space optical communication terminal, which emits 4 watts of laser power at 1.5 micron in the standard telecom band, using a 22 centimeter aperture telescope. And this signal has been already received in California at the Las Palomas Observatory using a 5-meter telescope. And another telescope that is being used now for that purpose is a 2.3 Aristarchus telescope at Helmos Observatory on the Peloponnese. And now things become very interesting, because if we do the numbers, and I will show you some numbers later on, then for those parameters, the amount of light we can receive from our transmitter is of the order of hundreds of thousands of photons per second. And now the question is, how much information can we encode using such a weak light beam, which actually boils down to the question, to the following question. So we are dealing in the so-called photon-starved regime, where the average photon number per slot is much less than 1. Now, if we ask what is the capacity limit, and we don't have any constraints on the bandwidth, on the slot rate, then actually we can check what is happening in the limit of the signal strength going to 0. And then we find out that our capacity is proportional to the mean photon number per slot, which makes sense, times some factor. And this factor actually tells us how many bits of information we can encode in one received photon, all right? So what we are fighting for is high photon information efficiency. Now, how much time do I have? Oh, okay. So how to do this in practice? There is a modulation format that is well known has been well known for years. Namely, we take a single light pulse and put it in a number of otherwise empty slots. And if we have even if we have a very weak light pulse, it is enough that it generates just one photo count to recover this information. Of course, bad things may happen, because if the pulse is very weak, it may not generate a photo count at all, and then we are dealing with erasures. Or if we have background noise, it may generate a photo count in the wrong place. Speaking of which, this expression that I showed you here actually works in a scenario that doesn't really have much to do with actual implementations of PPM. The reason for that is that our noise is usually broadband, and if we do standard filtering, namely like an optical interference filter and temporal gating, we pick up noise from other temporal modes that are orthogonal to the mode carrying our signal. So actually, this is not really directly relevant to what people measure in in how people detect such signals. But in principle, there is a very beautiful technique that is being developed by the group of Christine Silberhorn in not far from here at the University of Paderborn and by Mike Kramer at the University of Oregon, of this mode selective up conversion, which from the point of view of an electrical engineer would mean that we can implement an or optical matched filter without optical to electrical signal conversion, okay? This technique is maturing, and we did some calculations, some estimates telling us that in principle, we could, using this mode selective photon counting, could push information rates, for example, for the psych emission, but also it should enable daytime operation because of this much better mode selectivity. Speaking of which, background noise is also huge nuisance in quantum key distribution, especially satellite to ground. And in many cases, it is recognized that this background noise is like the limiting factor for key distribution. And this technique could be also used to reduce substantially the background noise in satellite to ground QKD links. Speaking of which, and I would like to use my last 5 minutes on that, well, we are hearing a lot about quantum key distribution, and it is a very, very hot topic. But one statement I would like to make, for which I hope I will not be killed, is that very, very popular topic of quantum key distribution is just a subset of physical layer security solutions. And what I'm realizing is that physical layer security kind of has been for many years. Those who do practical networks kind of stay away from that because they say that they would have to change the architecture of networks, and maybe it's better to stay with cybersecurity in the digital layers and so on and so on. So the point I would like to make is that perhaps instead of starting from a, as we would say in Polish, high C from music, as I don't know if you have this in German too, that you start from something very ambitious at the beginning. Maybe we should also look at other PLS solutions from the quantum perspective that do not offer the level of security as QKD, but we are starting to recognize that QKD security has a lot of issues related to implementation. There are many things to worry about. And I think the view that is now becoming dominant is that any PLS solutions, like also QKD, should be combined with enhanced, with upgraded solutions in the digital layers just to create another defense line. So when it comes to PLS, one very simple scenario is when the eavesdropper receives less of a signal than the legitimate users, and we know the wiretap channel technology. What I would like to point out is that we really have to worry if the eavesdropper has some quantum capacity, because then the trade-offs between the legitimate user and the unauthorized users, they change a lot. But what I would also point out is that if we are worried about a scenario when the eavesdropper receives much more signal than the legitimate user, but is not able to disturb the signal going to the legitimate user, we can actually do sort of key distribution using much simpler means than quantum key distribution. To avoid confusion, we call it optical key distribution, because basically it is based on intensity modulation and direct detection and intensity measurement. The trick to generate a secure key is kind of similar to that is being used in continuous variable QKD. But what is really nice is that it can be integrated with IMDD data transmission without using additional wavelength channel, without time division multiplexing. We can basically piggyback on IMDD data transmission, and we can do the same trick in space. Also, if we are dealing with very, very, very weak signals, then we can do this kind of intensity modulation at the few photon level to generate a secure key. And we have also done some simulations how much key using the OKD technique could be generated for links from LEO satellite to ground. And with that, I would like to thank you for your attention.
Thank you very much, Konrad. Yeah, we have a question from Anton.
Thank you very much for a very interesting talk. I have a question about this last part of physical layer security in this conception of wiretap channel. How do we know the possibilities of Eve in quantum key distribution? We can estimate it from observable data and uncertainty relations. But here, maybe it's a more
this is a very good question. So actually, QKD assumes the worst case scenario. We estimate the amount of information picked up by Eve from the properties of the channel from Alice to Bob, which makes QKD very secure and very difficult to implement at the same time. Mm-hmm. But imagine, for example, satellite to ground communication. We have our ground station. We know, let's say we observe our satellite. So we know that there is no high altitude flying platform interfering with the signal. And the only thing we are worried about is that the adversary sets up another ground station beyond the area that is under our control. And we make an assumption how much signal that adversary can collect.
So there is a fundamental, one can impose some, not fundamental, but some limitation of Eve's capability. If she is not flying near your satellite and just also on the ground, that it's in place. Thank you. That's
and I would be the last person to advocate replacing current cybersecurity solution with PLS. I think what we should do, we should combine PLS with digital layer security.
Okay, thank you.
Great talk, Konrad, as usual. That I completely agree with you on pretty much everything you said. I just want to mention that unlike quantum key distribution, there has been at least 2 more decades of research on PLS, as you know. I mean, Weiner originally came up with his famed expression for the wiretap channel capacity, I think in 1972. And really, it's, I suppose BB84 would be the starting point for the quantum key. So maybe not 2 decades, maybe a decade and a half, but they had a head start. And they also had the advantage of having physical devices that are actually not on paper but work. Radio has been around since, well, depends on, I think in Poland they had their own inventor of radio. In America it's Marconi, I don't know, in France somebody else, and so everybody has invented radio at some point, right? I really like this idea of trying to use the PLS solutions in the quantum world. I think it's not being done properly. One thing I want to point out is what this made me think of is Dennis Gecko's work on the everlasting secrecy, where you actually are using the fact that there is limited bandwidth that the adversary will always have to deal with, and choose a code according to that. That hasn't, to my knowledge, been really tried in optical domain. We should do it. I don't know, something like that would be interesting. It's difficult to implement physically, though. But yeah.
Yeah, I apologize. I mean, the list of references is terribly incomplete. There is also interesting work, for example, by Angeles Vasquez Castro from Barcelona. So I think my suggestion would be to look more broadly into the PLS just beyond QKD, not only to go into very exotic versions of QKD, but do something maybe simpler that later on could be upgraded. Okay, because also the interface between key generation and key management. I mean, key management is also a tricky issue.
Maybe I can also ask a question. So are you aware of any use of these wiretap code systems in practice?
As Konrad mentioned, for the same reason that quantum key distribution is not terribly useful, no matter what many companies, I'm sorry, Mark, would like you to believe. It's oh well, it's fine. But some of your colleagues may disagree with me, but there is a reason why digital crypto is used. It works. It's simple. It's interoperable. It's doesn't depend on physical implementation of a device, and so no, PLS stuff has also been basically in the lab and relegated to very few.
You know what for the past 10 years we've been trying to interact with optical communication community. We've made a lot of friendships and we've done some joint work. But one thing that made me really depressed is that the modern optical communication is based on the idea to keep the optical layer as simple as possible. Basically, you get out of the optical layer as soon as you can, and you do everything else digitally because it's so much easier, it's so much more versatile, it's so much less problematic. So, which at some point made me ask question whether I could be useful at all in this business. So, I think this is a very important question. I mean, how to make PLS solutions compatible with this attitude of this paradigm.
One place where PLS solutions have been actually implemented, not in the sense of communication, but for sensing. Radars use all sorts of physical waveform designs for detection tasks that range from requiring protection from spoofing to just using the properties of the targets that they're looking for. So that's where I personally think that the quantum key distribution like methods, quantum methods in general, are going to go to. I don't know whether Konrad, you have anything to add about that.
Yeah.
No eavesdropper.
Yeah, there was one more question there.
Last question.
If we have, sorry to keep you away from lunch.
Mine is maybe more contribution to this discussion or something to the question whether the wiretap model is used in practice. I mean, the wiretap model is not necessarily just on a physical layer. You can have a wiretap channel on any layer, and in those secret sharing schemes like Shamir secret sharing or so, I think this is like information theoretically secure secret sharing is based on the wiretap model. And there, for example, an assumption is that you only have access to 2 out of 3 servers or something. So actually, let's say people who think they're more practical than us don't necessarily have completely different assumptions than us. The other thing that I was thinking of is would you think that there is a possibility to basically use those complicated solutions just to upgrade your channel, or basically combine a simpler channel for most of it and just do some twist, adding some quantum secure thing to get maybe some to get your wiretap channel good enough or realistic enough that people believe you have it or something. Because I mean, in the end, I think the objection against physical layer security is often the assumption is too strict. You don't have a wiretap channel in reality. And then if you can have an additional, just small channel that is realizable, that gives you a wiretap channel, for example, maybe that's something that it's more realistic.
Yeah, so I think one question is who's gonna pay for it, because a lot of optical communication these days has become a commodity. I mean, would you pay, let's say, 100 euros more per month for physical layer security in your for your terminal in your apartment? Probably not. Would you pay would you pay €1 per month more if I tell you that your neighbors will not be able to eavesdrop on what comes to your place? Maybe yes. So we really have to, I mean, one issue is the cost, and the second issue is to be very, very precise. What is the enhancement in security?
Okay, thanks a lot, Konrad, also for the discussion among the audience.